Hi future engineers! Today, we will talk about thermodynamic cycles. There are 6 cycles to be discussed in total, so make sure to check them all, and they are as follows: Carnot cycle, Otto cycle, diesel cycle, dual cycle, Stirling cycle, and Ericsson cycle. But for today's video, the discussion is all about dual cycle. Don't be lazy and grab your scientific calculator. So if you're ready, let's begin. Dual combustion cycle. Let me first introduce to you Gustav Drinkler. Dual combustion cycle was first introduced by a Russian-German engineer named Gustav Drinkler, who never claimed to have developed the cycle though. Dual combustion cycle is sometimes known as the combined SI or spark ignition and CI or compressed ignition engine cycle. Dual cycle or limited pressure cycle is a thermodynamic cycle that combines the Otto cycle and the diesel cycle. Heat is added partly at constant volume, which is isochoric or isometric process, and partly at constant pressure, which is isobaric process. The significance of which is that more time is available for the fuel to completely combust. Because of lagging characteristics of fuel, this cycle is invariably used for diesel and hotspot ignition engines. Dual combustion cycle consists of 2 isentropic or reversible adiabatic, 2 isometric, and 1 isobaric processes. Before we proceed to the discussion of dual cycle, let me just give you a trivia. Did you know that the name dual cycle is derived from the fact that it is an integration of both the Otto and diesel cycle? We can also call this cycle as mixed cycle. Like what I've said earlier, dual cycle is a combination of spark ignition or Otto cycle and compressed ignition or diesel cycle. To continue with our discussion about the dual cycle, I'm going to discuss the PV and TS diagram of this cycle. First is process 1 to 2, which is reversible adiabatic compression process. The gas is compressed adiabatically from state 1 to state 2, as the piston moves from intake valve closing point 1 to top dead center. The surroundings do work on the gas, increasing its internal energy and compressing it. On the other hand, the entropy remains unchanged. Next is process 2 to 3, or isometric heat addition process. In this phase, there is a constant volume heat transfer to the air from an external source while the piston is at rest at top dead center. This process is similar to the isochoric process in the Otto cycle. It is intended to represent the ignition of the fuel-air mixture injected into the chamber and the subsequent rapid burning. Next is process 3 to 4, which is isobaric heat addition process. In this phase, there is a constant pressure heat transfer to the air from an external source while the piston is moving toward the volume at point 4. Next is process 4 to 5, or reversible adiabatic expansion process. In this process, the gas expands adiabatically from state 4 to state 5, as the piston moves from volume at point 3 to bottom dead center. The gas does work on the surroundings and loses an amount of internal energy equal to the work that leaves the system. And lastly, process 5 to 1, which is isometric heat rejection process. In this phase, the cycle completes by a constant volume process in which heat is rejected from the air while the piston is at bottom dead center. The working gas pressure drops instantaneously from point 5 to point 1. The exhaust valve opens at point 5. The exhaust stroke is directly after this decompression. As the piston moves from bottom dead center or point 1 to top dead center or point 0 with the exhaust valve opened, the gaseous mixture is vented to the atmosphere and the process starts anew. Just an additional tip. When we are solving a problem, you can check on the diagram whether the value of your answers for the PVT cycle are accurate. For the pressure, the maximum value should occur at point 3 or point 4 since they are equal, and the minimum value should occur on the pressure at point 1. For the volume, the maximum value should occur at point 1 and 5, while the minimum value should occur at point 2 and 3. And last, for the temperature, the maximum value should occur at point 4 and the minimum value should occur at the point 1. Let us now proceed to the detailed analysis of dual combustion cycle. Dual combustion cycle starts with reversible adiabatic compression process. In this process, the entropy at point 1 and 2 is constant, so we can say that S1 is equals to S2, or P1V1 raised to K is equals to P2V2 raised to K. We know that the simplified form of P1V1 raised to K equals to P2V2 raised to K is T2 over T1 equals to V1 over V2 raised to K minus 1 equals to P2 over P1 raised to K minus 1 over K. The simplified form of V1 over V2 raised to K minus 1 equals to P2 over P1 raised to K minus 1 over K is P2 over P1 is equals to V1 over V2 raised to K. And looking at the PV diagram at point 1 to 2, the air is compressed. So the compression ratio is RK is equals to V1 over V2. So we can now rewrite the equations T2 over T1 equals to V1 over V2 raised to K minus 1 to T2 over T1 equals to RK raised to K minus 1. And P2 over P1 equals to V1 over V2 raised to K is P2 over P1 equals to RK raised to K. At point 2 to 3 or isometric heat addition process, the volume is constant. So, V2 is equals to V3, or P2 over T2 is equals to P3 over T3. In this cycle, we have an additional ratio which is the pressure ratio. It is simply the ratio between the pressure at the end over the pressure at the beginning of isometric heat addition process. So we can say that Rp is equals to P3 over P2. Since V2 is equals to V3, we can also rewrite the pressure ratio as Rp is equals to T3 over T2. The heat added during isometric process, take note that UA1 is equals to delta U, while delta U is simply equal to mCV multiplied by T3 minus T2. So, QA1 is equals to mCV multiplied by T3 minus T2. Next is at point 3 to 4, which is isobaric heat addition process. In this process, the pressure is constant. So we can say that P3 is equals to P4, or V3 over T3 is equals to V4 over T4. In this process, we have a cutoff ratio. It is the ratio between the volume at the end over the volume at the beginning of the isobaric heat addition process. So RC is equals to V4 over V3. Since P3 is equals to P4, we can also rewrite the cutoff ratio as RC is equals to T4 over T3. For the heat added during the isobaric heat addition process, QA2 is equals to mCP multiplied by T4 minus T3. At point 4 to 5, which is reversible adiabatic expansion process, S4 is equals to S5, or P4V4 raised to K is equals to P5V5 raised to K. And we all know the relationship when we say reversible adiabatic. So T4 over T5 is equals to V4 over V4 raised to K minus 1 equals to P4 over P5 raised to K minus 1 over K. So now, let me show you the derivation for the temperature at point 5. Take note that V5 is equals to V1, V4 is equals to V3 RC, V3 is equals to V2. So, V4 is equals to V2 RC. Then T4 over T5 is equals to V1 over V2 RC raised to K minus 1. Also take note that V5 is equals to V1, V4 is equals to V3 RC, V3 is equals to V2. So, T4 over T5 is equals to RK over RC raised to K minus 1. Also take note that T4 is equals to T1 RK raised to K minus 1 RP RC. So, T1 RK raised to K minus 1 RP RC is equals to T5 multiplied by RK raised to K minus 1 over RC raised to K minus 1. Then simplify. Therefore, the temperature at point 5 is equals to RP RC raised to K. At point 5 to 1, which is isometric heat rejection process, the volume is constant from point 5 to point 1. So, V5 is equals to V1, or P5 over T5 is equals to P1 over T1. For the heat rejected during the isometric heat rejection process, QR is equals to mCV multiplied by T5 minus T1. For the total heat added is simply the sum of heat added during the isometric heat addition and isobaric heat addition. So, QAT is equals to QA1 plus QA2, or QAT is equals to mCV multiplied by T3 minus T2 plus mCP multiplied by T4 minus T3. Next is for mean effective pressure. MEP is equals to net cycle work over volume displacement equals to W net over Vmax minus Vmin. Volume displacement is simply the difference between the maximum volume and the minimum volume. For the net cycle work is equal to the total heat added minus the heat rejected, or W net is equals to QAT minus QR. For the percent clearance, C is equals to Vc over Vd equals to V2 over Vmax minus Vmin. Take note that there is a relationship between percent clearance and compression ratio. Therefore, Rk is equals to 1 plus C over C. For the cycle thermal efficiency, it is equal to the net cycle work over the total heat added, or EC is equals to W net over QAT equals to QAT minus QR over QAT. We know that W net is equals to QAT minus QR. So, the simplified form of this equation is equals to 1 minus QR over QAT. There is another formula for cycle thermal efficiency. So, let me discuss the derivation of that formula. Take note that QR is equals to mCV multiplied by T5 minus T1, and QAT is equals to mCV multiplied by T3 minus T2 plus mCP multiplied by T4 minus T3. Then, EC is equals to 1 minus quantity of mCV multiplied by T5 minus T1 over mCV multiplied by T3 minus T2 plus mCP multiplied by T4 minus T3. Cross out the similar terms, then simplify. Also take note that Cp is equals to Kcv, T2 is equals to T1Rk raised to K minus 1, T3 is equals to T2Rp equals to T1Rk raised to K minus 1 Rp. Then T4 is equals to T3Rc equals to T1Rk raised to K minus 1 Rp/Rc. And last is T5 equals to T1Rp/Rc raised to K. Then Ec is equals to 1 minus quantity of T1 multiplied by Rp/Rc raised to K minus 1 over T1Rk raised to K minus 1 multiplied by Rp minus 1 plus Kt1Rk raised to K minus 1 Rp multiplied by Rc minus 1. Cross out similar terms and simplify, and it will become Ec is equals to 1 minus quantity of Cv multiplied by T1Rp/Rc raised to K minus T1 over Cv multiplied by T1Rk raised to K minus 1 Rp minus T1Rk raised to K minus 1 plus Kcv multiplied by T1Rk raised to K minus 1 Rp/Rc minus T1Rk raised to K minus 1 Rp. Cross out again the similar terms. Therefore, the formula for the cycle thermal efficiency is Ec is equals to 1 minus quantity of Rp/Rc raised to K minus 1 over Rk raised to K minus 1 multiplied by Rp minus 1 plus Krp multiplied by Rc minus 1. So now, let's try to solve a sample problem. At the beginning of compression in an ideal dual combustion cycle, the working fluid is 1 pound of air at 14.1 psi absolute and 80 degree Fahrenheit. The compression ratio is 9. The pressure at the end of the constant volume addition of heat is 470 psi absolute, and there are added 100 BTU during the constant pressure expansion. Determine the following: PVT cycle at each points, Rp and Rc, net cycle work and heat rejected, cycle thermal efficiency or EC, mean effective pressure or MEP, and percentage clearance or C. For the given, we have a mass equals to 1 pound of air, pressure at point 1 equals to 14.1 psi absolute, temperature at point 1 equals to 80 degree Fahrenheit plus 460 equals to 540 Rankine. Pressure at point 3 is equals to 470 psi absolute, Rk is equals to 9, and Qa2 is equals to 100 BTU. For the solution, at point 1, we have a given values of pressure at point 1, which is 14.1 psi absolute, temperature at point 1, which is 540 Rankine, and mass of air, which is 1 pound. Since we have a given pressure, temperature, and mass of air, we can now solve for the volume at point 1. We will use the formula PV is equals to MRT. So for the volume at point 1, V1 is equals to MRT1 over P1. Substitute the given values of pressure, temperature, mass of air, and the constant R of air, which is 52.34 foot-pound per pound R. So, V1 is equals to 1 pound multiplied by 53.34 foot-pound per pound R multiplied by 540 Rankine over 14.1 pound per square inch multiplied by 12 inch per 1 feet raised to 2. So, we we multiply 14.1 pound per square inch to 12 inch per 1 feet raised to 2 to convert the inch to feet for the cancellation of units. So, volume at point 1 is equals to 14.186 cubic feet. At point 2, since we have a given value of compression ratio and we already solved the value of volume at point 1, we can now solve for the value of volume at point 2 using the formula of compression ratio, which is Rk is equals to V1 over V2. Substituting the values, V2 is equals to 14.186 cubic feet over 9. So the volume at point 2 is equals to 1.576 cubic feet. Next is solving for the temperature at point 2. We can use the formula T2 over T1 equals to V1 over V2 raised to K minus 1, or T2 over T1 equals to Rk raised to K minus 1, since Rk is equals to V1 over V2. Take note that the formula that you're going to use is based on the given. In this case, we can use any of the two formulas. So let's try to use T2 over T1 equals to V1 over V2 raised to K minus 1. So, T2 is equals to T1 multiplied by V1 over V2 raised to K minus 1. Substituting the values, T2 is equals to 540 Rankine multiplied by 14.186 over 1.576 raised to 1.4 minus 1. Take note that the constant specific heat capacity of air is 1.4. So the temperature at point 2 is equals to 1300 Rankine. Solving for the pressure at point 2, we can use the formulas P2 over P1 equals to V1 over V2 raised to K, or P2 over P1 equals to Rk raised to K, since Rk is equals to V1 over V2. But for now, let's try to use P2 over P1 is equals to Rk raised to K. So, P2 is equals to P1 Rk raised to K. Substituting the values, P2 is equals to 14.1 pound per square inch multiplied by 9 raised to 1.4. So the pressure at point 2 is equals to 305.6 psi absolute. At point 3, we have a given value of pressure, which is 470 psi absolute. Since process 2 to 3 is isometric heat addition process, therefore, volume at point 3 is equals to volume at point 2 equals to 1.576 cubic feet. Solving for the temperature at point 3, we can use the formula P2 over T2 is equals to P3 over T3. So, T3 is equals to T2 multiplied by P3 over P2. Substituting the values, T3 is equals to 1300 Rankine multiplied by 470 over 305.6. Therefore, temperature at point 3 is equals to 1999 Rankine. Take note that there are alternative formula to use. In this case, we can also use PV is equals to MRT to solve for the temperature at point 3. So, T3 is equals to P3V3 over MR. Substituting the given values, T3 is equals to 470 pound per square inch multiplied by 12 inch per feet raised to 2 multiplied by 1.576 cubic feet over 1 pound multiplied by 53.34 foot-pound per pound hour. And we will come up with the same answer for temperature at point 3, which is 1999 Rankine. Since we got the same answer, it proves that alternative solutions are applicable to any other thermodynamic processes. At point 4, since process 3 to 4 is isobaric heat addition process, Therefore, process at point 4 and point 3 are equal. So, P4 is equals to P3 equal to 470 psi absolute. Solving for the temperature at point 4, since the value of heat added at process 3 to 4 is already given, we can use the formula QA2 is equals to mCp multiplied by T4 minus T3, or T4 is equals to QA2 over mCp plus T3. Substituting the given values, T4 is equals to 100 BTU over 1 pound multiplied by 0.24 BTU per pound R plus temperature at point 3, which is 1999 Rankine. So, the temperature at point 4 is equals to 2416 Rankine. Take note, for the Cp of air, we can solve it by using the formula Cp is equals to R multiplied by K over K minus 1. Since we already know the constant values of R and K of air, so Cp of air is equals to 0.24 BTU per pound R. Solving for the volume at point 4, we can use V3 over T3 is equals to V4 over T4. So, V4 is equals to V3 multiplied by T4 over T3. Substituting the given values, V4 is equals to 1.576 cubic feet multiplied by 2416 over 1999. So, the volume at point 4 is equals to 1.905 cubic feet. Next is at point 5. Process 5 to 1 is isometric. So, V5 is equals to V1, which is 14.186 cubic feet. Solving for the temperature at point 5, we can use the equation T4 over T5 is equals to V5 over V4 raised to K minus 1. So, T5 is equals to T4 multiplied by V4 over V5 raised to K minus 1. Substituting the given values, T5 is equals to 2416 Rankine multiplied by 1.905 over 14.186 raised to 1.4 minus 1. So, the temperature at point 5 is equals to 1082 Rankine. For the pressure ratio, there is also different formulas that we can use in solving the pressure ratio. But if you already have all the values of PVT at each points, you can now solve it using any of these, which is the Rp is equals to P3 over P2 or Rp is equals to T3 over T2. But for now, let's try to use Rp is equals to P3 over P2. Substituting the given values, Rp is equals to 470 over 305.6. So, pressure ratio is equals to 1.54. For cutoff ratio, again, there is also different formulas that we can use in solving the cutoff ratio. But if you already have all the values of PVT at each points, you can now solve it using any of these, which is Rc is equals to V4 over V3 or Rc is equals to T4 over T3. So now let's try to use Rc is equals to V4 over V3. Substituting the values, Rc is equals to 1.905 over 1.576. So, the cutoff ratio is equals to 1.21. For solving of heat rejected, we can use the formula Qr is equals to mCv multiplied by T5 minus T1. Then substituting the given values, Qr is equals to 1 pound multiplied by 0.1714 BTU per pound R multiplied by 540 Rankine minus 1082 Rankine. Therefore, the heat rejected is equals to negative 92.9 BTU. In solving for the net cycle work, we can use the formula W net is equals to QAT minus QR. But before that, we need to solve for the value of total heat added. The formula for solving total heat added is QAT equals to QA1 plus QA2. We can't solve for the total heat added yet because we don't have a value of the heat added during the isometric process. So, we need to solve first the value of heat added during the isometric process. Heat added during the isobaric process is already given, so that we just need to solve for the value of heat added during the isometric process, and we can use the formula QA1 is equals to mCV multiplied by T3 minus T2. Substituting the given values, QA1 is equals to 1 pound multiplied by 0.1714 BTU per pound R multiplied by 1,999 Rankine minus 1,300 Rankine. So, the value of QA1 is equals to 119.8 BTU. Since we already got the value of heat added during the isometric process, we can now solve for the total heat added by adding the heat added during the isometric process and heat added during the isobaric process. So, for total heat added, QAT is equals to QA1 plus QA2. Substituting the values, QAT is equals to 119.8 BTU plus 100 BTU. So, the total heat added is equals to 219.8 BTU. Now, we can solve for the net cycle work. For the net cycle work, W net is equals to QAT minus QR. Substituting the given values, W net is equals to 219.8 BTU minus 92.9 BTU. So therefore, net cycle work is equals to 126.9 BTU. For cycle thermal efficiency, let's use the formula EC is equals to W net over QAT. But we can also use the formula that we derived earlier. But for now, let's try to use this equation. So substituting the given values, EC is equals to 126.9 BTU over 219.8 BTU multiplied by 100%. So cycle thermal efficiency is equals to 0.5773 or 57.73%. For the mean effective pressure or MEP, we can use the formula MEP is equals to W net over VD, or MEP is equals to W net over maximum volume minus minimum volume. Substituting the given values, MEP is equals to 126.9 BTU multiplied by 778 foot-pound per 1 BTU over 14.186 cubic feet minus 1.576 cubic feet. We multiplied 126.9 BTU to 778 foot-pound per 1 BTU to convert BTU to foot-pound for the cancellation of units. So, MEP is equals to 7,829.358 pound per square feet multiplied by 1 feet per 12 inch raised to 2. So, MEP is equals to 54.37 PSI. And last, for percent clearance or C. To solve for the value of percent clearance, we can use the formula of compression ratio in relation with percent clearance, which is RK is equals to 1 plus C over C. Substituting the value of compression ratio, 9 is equals to 1 plus C over C. Therefore, percent clearance is equals to 0.125 or 12.5%. So I prepare an exercise problem for you so you can practice and apply all that you have learned from our discussion. I already included the correct answers so you can check whether your answers is correct or wrong. So that's it for today's discussion. I hope you learned something new. Don't forget to like and subscribe. Thank you for watching.